Now we're going to talk about colligative properties, which is the reason we needed to learn about molality in the first place. Have you guys ever made ice cream at home? Mm-hmm. Maybe you had an old-fashioned churn that you had to crank by hand, or probably one that's electric. You plug it in, and there's this cylinder where you put the milk and stuff, and it's got a paddle in there, and then there's a larger bucket, and you put ice out there, and you have to put salt on the ice. Why do you have to put salt on the ice? Because it makes it colder. Salt is going to lower the temperature at which that solution freezes to about -10 degrees Celsius. And this is something we're going to get to see firsthand next Tuesday when we make ice cream. Because part of that experiment is you put a bunch of ice into a Ziploc bag, and you take the temperature of the ice as it starts to melt. And what's the temperature when water in the solid and liquid states are together? What's that? The melting point or the freezing point, right? Which should be 0 degrees Celsius. And then you're going to pour some salt in there, mix it around a little, and you can watch the thermometer drop. And it'll go down to like -10. And if you feel it, you're like, oh yeah, that's colder. Doesn't that seem crazy? Because when you salt your potatoes, does that make them cold? No. But when you salt ice, that makes it cold. It's crazy. Yeah.
I had heard that that's why Fahrenheit is, why the freezing point of water is 32, because 0 is for salt water.
Yeah.
Salt water is 0 degrees Fahrenheit.
Yeah, it's interesting, to think about, well, because, all units are made up, right? And so where did those numbers on the Fahrenheit scale come from, right? So 0 on the Fahrenheit scale is a saturated saltwater solution. It's the temperature at which saturated salt water freezes. And I don't know where the 212 came from, but pure water will freeze at 32. So colligative properties, this freezing point depression, the depression of the freezing point is one of them. These are properties that depend on the number of particles that are dissolved. It doesn't matter what they are. This is kind of strange. It doesn't matter what the particles are. It just matters how many there are. There's a slight difference between using electrolytes and non-electrolytes, because a non-electrolyte, if you put in 1 mole of it, you get 1 mole of particles. But if you put in 1 mole of an electrolyte, like sodium chloride, well, that's going to separate into ions, sodium ions and chloride ions. So you're going to have 1 mole of sodium chloride, you're going to end up with 1 mole of sodium ions and 1 mole of chloride ions. So that's a total of 2 moles of particles from the electrolyte. So you have to pay attention to, is this an electrolyte or a non-electrolyte? So the first colligative property we're going to talk about is vapor pressure lowering. So we've talked about vapor pressure recently. So here we have a covered beaker. Let's pretend this is water. And the water's going to evaporate. And because it's trapped, the water here in the gas state is also going to be condensing. And this will come to a point of dynamic equilibrium where the vapor pressure here is dependent on the temperature of the water. Well, if we put some solute particles in here, those are going to get spread evenly throughout the water. Some of those solute particles will end up at the surface. In order for water to evaporate, it has to get to the surface, right? So if part of the surface now is solute particles instead of water molecules, that means it has less surface area, right? And the rate of evaporation depends on surface area. So if we have solute in here, that's going to lower the rate of evaporation. We've still got condensation coming here, and then because this is lower, this concentration will get lower, and eventually we will reestablish an equilibrium, but now we have fewer molecules in the gas state. So this is going to be a lower vapor pressure. Any questions? A more fundamental explanation is nature's tendency towards mixing, the increase in entropy. This is something you can do at home. So if you have a cake plate, it helps if it's some clear container so you can see what's going on here. So here we've got a beaker of pure water and a beaker of a concentrated solution. Could be sugar water, salt water, doesn't matter. So these are in the same covered space, and then you wait. And, you know, note to self, do this at home sometime. I've never done it at home. I don't know how long it takes. It's going to take a while. But what you'll see is that the level of water in the beaker of pure water goes down and the level of the solution goes up. Water molecules are actually traveling through the air from one solution to the other, from one beaker to the other. It kind of seems like a magic trick because you can't see it, right? You can't see what's going on. Oh, this is going to be a good day for training. We could beat the record.
Was it 11?
11. Mm-hmm. I had more yesterday, but that's because I was subbing for somebody, and so I was here for like all day. So, yeah. So what's going on here is the rate of evaporation from the pure water is faster than the rate of evaporation from the solution. And so the rate of condensation for both of these will be the same, and so we're going to end up with a net deposition of water into the concentrated solution beaker. So the vapor pressure of a solution is lower than that of the pure solvent. Raoult's law quantifies this. We can calculate the vapor pressure of a solution if we know the mole fraction of the solvent and the vapor pressure of the pure solvent. Notice this is mole fraction of solvent. So if this was pure solvent, what would its mole fraction be? If it was only solvent, the moles of solvent divided by the moles of solvent is going to be 1, right? So 1 times the vapor pressure of the pure solvent is going to give us the same number. If this solution, half the moles are something else, so we have 0.5 as our mole fraction, then we're multiplying the vapor pressure of the solvent by half. So this is very much like a percentage problem, right? The vapor pressure is directly proportional to the amount of solvent in the solution. There's another equation for the vapor pressure lowering, delta P. So this is how much the vapor pressure goes down. That uses the mole fraction of the solute. But I think this is the only one that we're going to see any problems for. Calculate the vapor pressure at 25 degrees C of a solution containing 55.3 grams ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at 25 degrees C is 23.8 torr. So we're going to use that equation that we just learned about, Raoult's law. So the vapor pressure of the solution is going to equal the mole fraction of the solvent, H2O, times the vapor pressure of the pure solvent. Well, they gave us the vapor pressure of pure water. We're trying to find the vapor pressure of the solution. So what we're missing here is mole fraction of water. Why is 25 degrees Celsius in there? Do we need to use that? There's no T's in this formula, right? We don't need to use that number in a calculation. But if we're using the vapor pressure, depends on the temperature. So if we're looking at the solution at 25 degrees Celsius, then we need to look at the vapor pressure of pure water at the same temperature. That's the only reason that's in there. So the mole fraction of water, mole fraction is the moles of the thing you're interested in divided by the total number of moles, right? So this will be moles of H2O divided by moles of H2O plus moles of the other thing. I'm going to call him EG, ethylene glycol. So we can find the moles of ethylene glycol because they gave us the mass and they gave us the chemical formula. So 55.3 grams of EG, ethylene glycol. Again, I want to multiply by moles and divide by grams. And then I have to calculate the molar mass here. So there's 6 hydrogens in there, times 1.008. And there's 2 carbons times 12, and there's 2 oxygens, times 16. 62.068. This is 0.89096 moles of ethylene glycol. Bless you. So that's the number that goes in here. So this is a mole fraction of 0.94671. Mole fractions can't be less than 0, can't be more than 1. So that's my mole fraction of water. And so the pressure of this solution is that fraction of the vapor pressure of pure water. 23.8 total. The unit on this pressure will be whatever the unit on the vapor pressure of the pure solvent is. Any questions? So when we have a non-volatile solute, like an ionic compound or something, that's, oh my goodness. I have to do that to the door. It's the only way it closes, but it feels good. Okay.
You can't swipe.
Anyway, if it isn't one thing, it's another, and several of its close relatives. So when we have a volatile solution, it's going to get in the way of the solvent evaporating, but the volatile solute is also going to evaporate and contribute to the total vapor pressure. So we can talk about ideal solutions and non-ideal solutions. Ideal solutions follow Raoult's law. Doesn't matter what the mole fraction is, they're going to follow Raoult's law, and the total pressure above the solution is going to be the partial pressure from each of those parts of the solution. Non-ideal solutions don't follow the law, and that's because of interactions between the solute and the solvent particles. So the first graph shows an ideal solution. So we're looking at the mole fraction of A. These solutions have component A and component B. So when we have 0 of component A, the vapor pressure of A is 0. When we go all the way to this end, where we have a mole fraction of 1 for A, then this is the vapor pressure of pure A. Over here, if we have no A, that means we must have all B. So there's the vapor pressure of pure B, and we see that goes down as the mole fraction decreases. The purple line is the total vapor pressure of the solution, which is just adding the blue and the red line together. So that's what happens if there's no interference by these interactions between the particles. Here we're looking at strong solute-solvent interactions. So here you can think of the solute and the solvent particles like each other, right? They're like, oh, I kind of like you. And so what's going to happen is that less of each of those components is going to evaporate because they're distracted by these other particles. Well, I don't really want to leave. I kind of like it here. So some of them leave, but not as many. And so we see that the vapor pressure of each component drops below what's predicted by Raoult's law. And so when we look at the total vapor pressure, that's also going to be below what's predicted. The other case is when we have weak solute-solvent interactions. So here the particles are like, I'm not so sure about you, right? I think I'd like to leave. So they would prefer to get out and evaporate. And so here we see the vapor pressure for each component bulging above what's predicted, and so then the total vapor pressure also is going to bulge. If we look at a phase diagram, we can draw some new lines here, understanding that vapor pressure lowering is going to happen at all temperatures. So here is for the solution, and here is for the pure solvent. So the vapor pressure of the solution is lower, and so its curve is going to extend out here. The boiling point, remember, is where the vapor pressure of the liquid is equal to atmospheric pressure. So there's the boiling point of the solvent. When we've added a solute to it, now the boiling point gets higher. Over here, we see there's the freezing point, and the freezing point moves to the negative direction. So it becomes lower. So we're talking about freezing point, depression, boiling point, elevation. It's one of those things you have to remember. Do they both go up? Do they both go down? Do they go towards each other? Do they go away from each other? They're going to move away from each other. This connection doesn't work for me, but a lot of people don't like the cold weather, right? So freezing makes you depressed, right? It's like, man, it's getting cold outside, and it's not enough sun, it's depressing. So freezing point is depression, and then boiling point is elevation. So we have a lower melting point and a higher boiling point for the solution. So here is the equation to calculate the freezing point depression. So delta TF here is the change in the freezing point. It's not the new freezing point, it's the change in the freezing point. And that is equal to the molality of the solution times a constant. And that's the freezing point depression constant, and what value that has will depend on what your solvent is. Delta TF is usually reported as a positive number, even though freezing point depression, the change is negative, but it's always reported as a positive number. So we just have to remember that. Here's a table showing several different solvents, their normal freezing points, normal boiling points, and here's the freezing point depression constant. So for water, that freezing point depression constant is 1.86. Calculate the freezing point of a 2.6 molal aqueous sucrose solution. Before I forget it, 1.86 degrees Celsius per molal. That's from the table in the previous slide. Our equation is that the change in the freezing point is equal to the molality times the freezing point depression constant. Unlike in lots of other examples, they're not making us calculate the molality. I guess they figure they tortured us enough. They're just giving it to us, right? So that's the molality right there. 2.6 molal, multiply it by that constant. The molalities cancel out. 2.6 times 1.86, 4.836 degrees Celsius. Is that the freezing point? That's the change in the freezing point. So this is the change in the freezing point. So we need to know the freezing point of the pure solvent in order to calculate the new freezing point. And when we're dealing with negatives, sometimes it's helpful to draw a picture. This is a very bad picture of a thermometer. There's the alcohol up the middle, and here is 0, and here is 100. Well, where does water usually freeze?
0.
At 0, right? So that's the normal freezing point, and this is the freezing point depression. So the temperature is going down that much. So we need to go down 4.836. So the new temperature is negative 4.8 degrees Celsius. So a 2.6 molal aqueous sucrose solution will freeze at negative 4.8 degrees. Questions?
You knew to start at 0 because of the aqueous part?
Yeah. I knew to start it at 0 because this says aqueous, which means the solvent is water. Yeah. And if, I do expect you to remember that the freezing point of water is 0 and the boiling point is 100. I do expect that. I don't expect you to remember any of the rest of those. Boiling point elevation, same kind of formula. The change in the boiling point is the molality times a constant. This is called the boiling point elevation constant. So we have this picture of someone putting antifreeze into their radiator. Why don't we use pure water? You can in a pinch, but it's not going to work as well. adding antifreeze, which contains ethylene glycol, or there's other types now, you're adding a solute to the water, and that causes the freezing point to go down, and it causes the boiling point to go up. So around here, we don't really care so much about our radiator freezing. In Minnesota, that's a big problem, actually. But in the summer, you don't want the water in your radiator boiling, right? Because that builds up a lot of pressure, and then the cap on the radiator has a release valve, and that's when you got these billows of steam coming out of your car, and that's a signal that, yes, you should pull over right away. And don't lift up the hood, and don't open the radiator. Just wait. Walk away, go play on your phone or something. Give it some time. It's too hot. But adding the antifreeze means that it boils at a higher temperature. So that's good. Calculate the boiling point of a 3.6 molal aqueous sucrose solution. Because I just lectured on this yesterday, I remember that the boiling point elevation constant for water is 0.512. It's not something I usually remember. So, nope, that's not right.
Where is that stuff again? On a chart?
Yeah,
Oh, this chart.
right here. So they're giving us the boiling point stuff and the freezing point stuff all on the same table.
We don't have to remember this.
You don't have to remember that, no. So the change in the boiling point is going to equal the molality times the boiling point elevation constant. So they told us what the molality was, 3.60 molal. We're going to multiply by our constant, degrees Celsius per molal. The molals cancel out. And here we get 1.8432 degrees Celsius. Well, my exams have a lot of multiple choice questions. This would be a great multiple choice question. That would be an excellent distractor, right? So you calculate it. Oh, I got a number that matches one. Yeah, it doesn't mean you did it right. We're not done yet, right? Does water boil at 1.8 degrees Celsius? No, it doesn't. It's going to boil at 100 plus this, right? So, our thermometer, so those are the boiling point and freezing points for water. The boiling point goes up, the freezing point goes down. So we need to go 1.8432 above that, and so it's 101. Let's see, 3 sig figs, 0.84. That's a pretty sad excuse for an 8.
I like when you get none of the answers.
Yeah. Yeah,
It's not there.
if you come up with an answer that's not one of the choices,
You messed up somewhere.
then it's like, okay, let's try that again. And I think it's really, really mean, and so I don't do it. I never have none of the above,
Oh, yeah, I don't like that.
like this. Because, you could give you all just garbage numbers and none of the above, but then, that's just like so risky
That's torturous.
as an exam taker, right? It's like, oh, I don't know. That's
You have
just,
to like be real confident in your numbers.
that's psychological cruelty. But I am warning you of a common mistake. You calculate delta T, either the freezing point depression or the boiling point elevation. You get a number, and it's really tempting to say, here's my answer. But you have to add to the boiling point or subtract from the freezing point to get the answer. Another colligative property is called osmotic pressure. Osmosis is the flow of solvent from a solution of lower solute concentration to one of higher solute concentration. This is the process by which drinking seawater causes you to become more dehydrated. the seawater has a higher salt concentration than the fluid in your cells does. And water is able to cross those semi-permeable membranes. And so the solvent is going to move from low concentration to high concentration. It's another one where I remember being confused about that as a student. And so what I finally came up with was, you've got these two different concentrations, and nature doesn't like them to be different, right? Because if you just put them in a container, they're going to spontaneously mix, right? So it doesn't want them to be different. So it's going to do what it can to lower the concentration of the more concentrated one. And you can do that by sending solvent into it to dilute it. So osmosis happens through a semi-permeable membrane, which allows some substances to pass, but not others. And biological cells have semi-permeable membranes. And those membranes are very important to the function of those cells. Yeah, say that 3 times fast. So here we have, when I was in college, we would have called this a U-tube, right? A U-tube, as opposed to like a J-tube. Well, that's a U-tube, but we don't call them that anymore because that's something else. Here is a tube that's shaped like a U, and there's a semi-permeable membrane in here separating the two sides. On one side, we have a solution, and on the other side, we have pure water. As time goes on, the water molecules are able to go through this membrane, but the solute particles are not. So water molecules are going to go from the left to the right. Water molecules are also going to go, from the right to the left and from the left to the right. They're also going to go in the other direction. But again, with the vapor pressure, we can think about these solute particles as getting in the way. They're kind of blocking part of the membrane. And so the movement of water from the concentrated side to the dilute side is going to be slower. So we're going to have a net migration from the more dilute side to the more concentrated side. So as that happens, the level on this side of the tube goes down because water is moving to the other side, and the water on that side, the level goes up because water's moving in there. As water moves in there, it's going to dilute that solution and bring it closer to being the same. This is a bit like a manometer. Remember, we looked at curved tubes with mercury in them. And if the heights of those columns were different, that meant there was a difference in pressure. So this is not a difference in atmospheric pressure, but it is a pressure difference, and this is called the osmotic pressure. So this is the pressure that you would have to apply to this side to prevent osmosis from happening. So osmotic pressure is the pressure required to stop the osmotic flow. Here's the equation for that. This is a yelling equation, it's all caps. Capital Pi is equal to molarity times the ideal gas constant times the temperature. We can use molarity here because we're not changing the temperature like we do with freezing point depression. So we got molarity, temperature in kelvins, of course, and here R is our old friend, 0.08206 liter atmospheres per mole Kelvin.
So it's still an actual pressure that's forced over an atmosphere.
It is a pressure,
Okay.
yeah. But it's not caused by a difference in the atmospheric pressure.
Okay.
It's caused by the flow of osmosis.
Okay.
So calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams ethylene glycol in 50.0 milliliters of solution at 25 degrees Celsius. So, got some ethylene glycol, we've got a volume, we've got a temperature. They're asking us for osmotic pressure in atmospheres. So, Osmotic pressure equals the molarity times the ideal gas constant times the temperature. Well, we're going to have to figure out the molarity, so I'm going to save that one for the end. R is the ideal gas constant. T is the temperature, 25 degrees Celsius. Convert that to Kelvin. And then we need to calculate the molarity. So we need moles of ethylene glycol divided by liters of solution. We have the solution volume in milliliters. Instead of writing milli, I'm going to write what milli stands for, which is 10 to the minus 3. So now we just need to do moles of ethylene glycol. So 1.50 grams of EG, and we previously calculated this. The molar mass was 62.068 grams per mole. Grams cancel out. .5 divided by 62.068. 0.024167 moles. Divide that number by 50 times 10 to the minus 3, and I'm going to get a molarity of 0.48334. So now I have all the pieces. 0.48334 moles per liter times 0.08206 liters times atmospheres per mole Kelvin times 298.15 kelvins. .8 atmospheres. On the useful information page, there are two values for R. One is this one with liter atmospheres, and the other one has joules in it. So how do you know which one to use? You look at the units. Okay. Here we have liters in the denominator, and we're looking for a pressure in atmospheres. If we use the value for joules, we're not going to come out with a pressure unit. Any questions?